All right, lesson 7.4, growth and decay. The exponential models that we looked at last class take us into some really neat applications about population growth and investment growth. Good to see our money get bigger, right? Okay. Last time when we were graphing our exponential models, we they had these pieces. Okay. And no matter what application that we're looking at today, all of them model the same pieces, just maybe written a bit differently to serve that application. So just a quick graph review of last time, okay? If I'm looking at y is equal to a times b to the x plus 0, okay? This x is my independent variable, my y, that's what's going into the equation, y is coming out as values. The 0, let's do that one in red, is representing the horizontal asymptote, which serves as the basement to our functions. All the applications that we look at today are going to have horizontal asymptotes of y is equal to 0. So, yep, that's easy enough. And the a value is always going to be our y-intercept. That's where our model is starting when x is 0. Okay, and last but not least is b is the growth factor or the decay factor. So when we look at our equations, it's super important to make that distinction at the beginning. Is this something that's going to be growing or is it going to be decaying? If it's growing, it's going to have your big fat plus sign right there, because any base that's exponential that has a base that's bigger than 1 is going to be exponential growth. If this number combined, 1 minus the r, turns out to be a number that's in between 0 and 1, it's going to be decay. So our first two examples, the population and the investments, are examples of exponential growth. All right? So let's do an example here. So example 1. The population of Johnson City in 2005 was $25,000. Since then, the population has grown at an average rate, so make sure you realize that's a rate, not a number, of 3.2% each year. And our job is to write an equation to represent the population of Johnson City since 2005, and then down here to do a more specific example where we're supposed to find the population, or I guess predict the population of Johnson City in 2015. So I think it's going to be a good idea to go ahead and make a little graph out of our information here, just so you can see that what we did yesterday is very similar, leading into what we're doing today. So our independent variable today is going to be t, and this changes the domain a little bit. The context of the problem has changed, because where yesterday we could have a domain of all real numbers for our graph, right? We draw that in, the arrows go up and out forever, okay? So, this arrow goes up and out forever, and this one goes out forever and gets super close to 0 when x gets infinitely negative, right? But today, in the context of this problem, our independent variable is time, and time has to be positive. It's time in years. And time is positive. So that means that we're only going to see this part of our picture. Our domain is only from 0 moving forward, right? On our y-axis, we are looking at population of Johnson City in people. Oh, I got to run a little bit of space out. That's okay. You get the idea. Okay, and so let's take a look. Looks like our initial amount is going to be 25,000 people. So that's our y-intercept. So in 2005, that's our 0 point here. That's when we're starting to measure the population of Johnson City. So as time goes on, after 2005, that population is going to grow, right? So our y-intercept 25,000, and our rate of growth is going to be 1 plus 3.2%. But here we have to make sure that when we do that 3.2%, we change it from a percentage into a number. So we're going to have to, it kind of shows what's going on here, but you're going to have to take your 3.2 and divide it by 100 to get that 0.032 that you have to put into the equation. Need numbers, not percentages, okay? So that gives us our general equation for any time t after 2005 in years. And down here we'll go ahead and actually find what the population of Johnson City is in 2015. So that's 10 years after. So on our graph here, 10 years after 2005 and 2015, we're going to plug that into our equation that we found up top. We're going to make sure that when we go to use the calculator, that we do the exponents before we do the multiplication. And when we do that, we're going to see that the population of Johnson City is going to end up to be 34,256 people. So it's really just giving me this number, right? As I put that t in, 10 years, representing 2015. Over here on the y-axis, I'm going to get that 34,256 people. So real simple. Remember, when you're going to, from your equation, you're going to say, is it growth? Population of Johnson City, since then it has grown, so that's going to be your 1 plus part. You're going to look for the rate as a number, 3.2% divided by 100, dump it in. You're going to look for your initial amount, which is your y-intercept. And then finally, they're going to ask you a specific question that you're going to apply to. So how many years after we start measuring in 2005 are we looking for the population? In this case, it was 10. Then just make sure in the calculator, you bang out your exponential part first before the multiplication, and you get the right answer. I'm going to get you guys just to pause the video right now, and I want you to go ahead and take a crack at this exercise, which is just exactly like the example that we just did, example 1. So give it a go, and I'll come back in a second. All right, let's see how you did. Let's look at the problem here. The population of the United States has been increasing at an average rate of 0.91%. If the population was about 303.146 million in 2008, predict the population in 2020. It's kind of ironic. It is 2020, so we can see how close we are. So let's go. What I did here is I just took a look and found what the initial amount was. So on the graph here, our y-intercept, 303.146 million, is right here when time is 0 at 2008. So let's just dump that in there. The 2008 is representing our t is equal to 0 years, right? And so I dump that into the A position here, times 1 plus, because my population is growing, by this amount. So I had to take the 0.91% divided by 100 to get 0.0091, all right? Then to go do the calculation, the difference between 2020 and 2008 was a time period of 12 years. I make sure I do my exponential calculation, or my exponent calculation, before I do my multiplication calculation here, and that lands me at 337.96 million people. So it's actually really simple. We look for our initial amount, we find our rate of growth and add it to 1, and then we apply the amount of time that that growth rate is going to work on our initial amount to find our total value after that amount of time. Let's take a look at an investment example, and we'll see how those same principles apply. So it says the Garcias have $12,000 that they invest in a savings account, and the bank pays 3.5% interest on savings accounts compounded annually. Find the balance in 3 years and state the interest earned. So our initial amount is this 12,000. That's what we're putting into the bank, or the Garcias are putting into the bank. They're calling that P. That's the principal. So in this formula that works for our investment stuff, our P is our initial amount, our A is our final amount. We're growing at 3.5%, so we've got our 1 plus, just like we did before with the population, and up here is our time in years. Okay, what's a little different here, and here's the growth rate. So we got to change that to a number. The 3.5%, we have to divide by 100 to make that into a number, the 0.035. But the part that's a little different in this one is this compounded idea. So compounded annually just means the amount of the number of times the bank will make an interest payment throughout the year. Okay, so if it says annually here, both of the ends, we're going to put 1 in both those places. So it ends up looking exactly like what we did in the last example, where we've just simply got 1 plus our growth rate times our 3 year, to the exponent of our 3 years here, right? Okay, where that changes a little, and we'll attach some videos that do compounding semi-annually, quarterly, and monthly. But for example, if that were to say monthly instead, that means that the bank's going to pay us interest 12 times per year. So our annual rate of 3.5% interest is going to get broken up into 12 pieces, meaning that I'm going to get every month, I'm going to get a 12 of 3.5%. Okay, so you just put the 12 here and the 12 here. So over 3 years, instead of getting 3 payments of interest, you're going to get 3 times 12, 36 payments of interest. It's just that every time it's a 12, you're going to get a little bit more money out of that. But again, another video for that a little bit later. But for this problem, we're compounded annually. So our ones here don't really change our formula enough. So let's just simplify our formula a little bit here. I've got my initial amount at $12,000. My growth rate, once I work all this out, just turns out to be 1.035. And the amount of time I want to see my investment grow, or the Garcias want to see their investment grow, is 1 times 3 is simply 3 years. Initial amount, growth rate, measured after a certain amount of time. And that ended up giving us $13,304.61. Okay, so we started here at 12 grand. Our growth rate after 3 years, 3 years, took us to our 13,304.61. Okay, and the actual interest that I earned is simply the difference between those two numbers, right? This is what I put in initially. This is what that grew to after 3 years. So the amount of interest that the bank actually paid us was $1,304.61. Right? I think what I'm going to do now is pause the video, and I'm going to let you guys set up number 2 there and give it a try. And so pause your video, do number 2, and then when you push play again, we'll take a look at the answers. So let's see what we did here. Our initial investment was $2,500. Boom. We know that our investment is going to grow, so we've got the 1 plus, our percentage turned to a number here, compounded annually, so divided by 1 all times that compounded annually, 1 times the number of years we're going to let it sit in the bank and grow, 4 years. So, simplified, 1.0525 comes out of this mess, all to the exponent of 4. Dump that in your calculator, and then multiply that amount by your 2,500 last, and we end up with $3,067.81. Let's look at number 3. Determine the principal if an investment grows to $100,000 after it was invested at an interest rate of 5.2% compounded annually for 12 years. Oh, this one's a little different, okay? Because instead of us looking for a final amount after 12 years, they're telling us how much we have after 12 years, and they want to find out how much should we actually put in before any time has passed so that we have $100,000 after that 12 years. So we'll just do the little switcheroo where the 100,000 takes the place of the A in our formula. The P is our unknown, and we set up the rest. So it's still growing at 5.2%. So let's dump that in. So 5.2 is a percentage, 0.052. It's compounded annually, so 1 payment per year for 12 years, right? And the only difference to calculating this is that we want to find P by itself. It's all multiplied by that, right? So in order to find P, we're going to divide both sides of this equation by this big mess. Okay, and P is going to end up being $54,426.59. So just isolate for P by dividing both sides by that quantity. We strongly suggest that you isolate P before you even pick your calculator up. So get it into this form so that when you go to use your calculator, you're only rounding once and you'll get your accurate dollar amount. Let's move on to exponential decay now, which works exactly like exponential growth except for one little difference. So let's look at an example. So the original price of a tractor is $45,000. The value of the tractor decreases, there's our key word, at a steady rate of 12% per year. So we want to set up the equation and then go find what the value of the tractor is after a certain amount of time. Exactly the same as exponential growth, except for the key word decreases. So in our formula here, instead of this number being bigger than 1 now, this entire growth rate, it's going to be a decay rate, and our number in there is going to be less than 1. Okay, so when you see decreases, that 1 minus the rate is what's really important to apply. So here, our initial amount, $45,000. As time goes by, the value of this tractor is going to go down. Okay, so 1 minus our 12% as a number, all to the T, is our new formula. So simplified, it looks like this: 45,000 times 0.88 all to the T. So I dump my 5 years into the T. This decay rate gets applied to this 45,000 5 times. Just remember your order of operations properly, and bango, you're going to end up with that tractor being worth $23,747.94 after the 5 years. So let's get you guys to try an example here. Go up. So pause again. Try this example, and when you're finished, push play and we'll see how you did. All right, how'd we do? In the first exercise there, it said the population of Bulgaria has been decreasing. There's our key word. at an annual rate of 0.89%, and if the population of Bulgaria was about 7.45 million in 2005, predict its population in the year 2025. So so our initial amount for 7.45 million. Our our rate of decay is going to be 1 minus 0.0089, which gives us 0.9911. Okay, so a number that's less than 1, so we know we're decaying, and we want to know what that population is going to be after 20 years. We started measuring the population in 2005, and we're finishing it 20 years later. So after 20 years, our population of Bulgaria is going to be 6.23 million people. Okay, so initial, decreasing, 1 minus, how much time, final answer. Number 2 is exactly the same. Mr. Gossel is a machinist. He bought some new machinery for about $125,000. He wants to calculate the value of the machinery over the next 10 years for tax purposes. If the machinery depreciates at the rate of 15% per year, what is the value of the machinery to the nearest $100 at the end of 10 years? So again, we see the word depreciate. Where is it? Here it is. We're depreciating. Here's our initial amount. Here's our rate of depreciation. So 1 minus 0.15 or 15%. And how much is this machinery going to be worth after 10 years? Okay. To the nearest $100. You got to really read the question carefully here. So you're going to get a little bit different decimal that comes out of this, but if we're calculating to the nearest $100 down here, $24,600. All right, on to our final example, number 3. A 4-year-old car is valued at $12,000. It is depreciated 12% for each year for 4 years. Determine its initial value. That $12,000 is an amount that is after the 4 years has passed, so it's our final amount. So let's set up the equation. Final amount of $12,000. We are looking for how much the car cost initially before any time had passed, and our depreciation rate, or our B value, I guess, in here, is going to be 1 minus 0.12, or the 12%, and the time that's going to hit that depreciation rate is 4 years. So to find our initial value, we've got to isolate for A by dividing both sides by, it looks like, 0.88 all to the 4. So this takes care of this, and our initial value rounded to the nearest cent is going to be $20,010.16. That is a wrap on exponential growth and decay. I hope you guys could follow that video clearly. I promise you I will try and do better next time. Take care.